our first exercise we'll practice is this one. So for the position control system shown in this figure below, position control, so shaft position here, and here is your desired position. Okay. Find the value of pre-amplifier gain K. You need to find K to yield a 9.5 overshoot. So you have a 9.5 overshoot in the transient response for step input. Okay, they ask you to use only frequency response methods. Don't use Rotlock's method. So how to find K that yields to 9.5 overshoot for a step input. So that's your system. You find the open loop transfer function, which is power amplifier times motor unload times the integrator, so shaft velocity, shaft position, and you get the open loop transfer function. You take it to the control system designer, or you can go over it from the app and then control system designer. Okay, so this time I don't want to use root locus. I just want to focus on frequency response method. So you need to find the gain that leads to the overshoot you need. Like peak response, it will give me the overshoot. So in this case I have 0 overshoot. So how to find that gain K that lead me to some overshoot? We know, like, increasing the gain will increase the overshoot, right? So look, here you have phase margin equal to, they give you the phase margin, they give you the gain margin. Okay, so what you did, you just click on it and drag it up and see. Alright, so let's see now, see how much it is. It is 7. When I drag it up, I have C equal, so my controller gain equals 7. G, of course, is the transfer function you have. H is 1, and also it's a good practice, as we said before, like I recommend you which one you need to use. Really, it's up to you. I use the 0 pole gain. Okay, just click and drag and look to your overshoot. The system getting faster, and now you have overshoot of 42. So again, let's refresh. 9.5 overshoot. So then go down, click and drag 9.5, so 15. Okay, so because I cannot, like, maybe I can click and go play with it, like maybe like this. 500, I need more. 600, 9.3, maybe 605. And that gives me 9.5. Okay, and this 9.5 is what you are looking for, the overshoot that you are looking for. It's obtained at 605 gain K, and that's the question. That's it. So here, simply find the value of the gain to yield to 9.5 overshoot for a step input, and we done with it. Okay, so you have it here in your document that I gave to you. All right. Okay, that's about exercise 1. So let's see now exercise 2. Well, you have same block diagram, but they ask you to design now a lag compensation design. Lag compensator, not simple gain. So use the body diagram to design lag compensator to yield a 10-fold improvement in steady state error over the gain compensated system while keeping the percent overshoot 9.5. Okay, you need to keep percent overshoot of 9.5 but you need to reduce the steady state error by 10. So this, as we are doing in root locus design, look at the system of type 1. So steady state error is 0 for a step input. So then here they are talking about a ramp input. Okay, so then KV, you need to steady state error, if you remember from the table, the state error equal 1 over KV in this case. Maybe if you want better view. Okay, so steady state error equal 1 over KV for a ramp input. So then KV, you can find KP limit 1s tend to 0 of s g of s. What g of s? G of s is the open loop. Well, usually we said no, it's a forward loop for a unity feedback system. That's the that's how we find G. If your system is not open loop, is not unity feedback, you need to convert it to a unity feedback system. As one exercise I showed you. So then your G of S is this block diagram times this system type 1. So that's why. So here your G of S. It's a lag compensator as we said. So then lag compensator, if you have in the S plane lag, so the past, so it is integral equivalent to pi. So the pole dominant the 0, and it's also good to practice how we do it in frequency domain. So this in S plane usually for root locus, but in frequency domain, if this is a frequency, usually frequency started from 0 to infinity. So then you have pole. So if this is a 0, then you have a pole somewhere, for example here, and a 0 here. See, pole smaller. So that's how we represent the frequency. P and C, omega C are the frequency as well, or we call it ZC here. Okay, PC and ZC. Those are frequency as well. Your pole is the frequency. Here is minus, here is positive. Like if this is minus 10, so then here you have 10 radian per second. That's how you represent a lag compensator in frequency domain. So, and the form still the same, S plus Z over S plus P. So you need to find a relation between Z and P, then assume P, you get Z, and so on. Alright. So it's a system of type 1, as we said. So we can find KV. Then after adding the compensator, we can find the new KV. How to find the new KV? Limit 1 s G of S times G lag. Now because you added lag compensator, then you can get the relation between ZC and PC. And we obtain a relation equal 10. So how did we obtain it? It's basically because KV new, it's known. How do we find KV new? We find KV new by the fact that KV new steady state error new equal 1 over KV new. And how to find the new steady state error? It's 10 times, it's tenfold the old steady state error. So you have the old steady state error, so you can find the new steady state error, and therefore you can find the new KV. Alright, so here for your reference, I wrote it for you. So then now you assume PC, usually you assume PC close to 0. Like if I assume PC equal 0.1, then ZC equal 10 times 0.1, which is 1. So then I can say my lag compensator equal S plus 1 over S plus 0.1, for example. And this is my lag compensator that is supposed to satisfy my requirements. So let's go and implement it. So now right click and a lag compensator. Well, I don't prefer to go this way, so I better to also no. From here I double click on it and add lag compensator 0 at 1 and pole at 0.1. Alright, so this is my S plus 1 over this my lag compensator. So this lag compensator will give me a steady state error of tenfold steady state error, because the relation between ZC and PC is 10. Am I satisfied the other requirement? What is the other requirement? Design a lag compensator to yield tenfold improvement in steady state error. Now you know, even if they don't tell you lag compensator, just they tell you design a compensator to yield a tenfold improvement in steady state error. Which controller improves the steady state error is the lag compensator. You can add PI controller as well. But here we decided to add lag compensator because we will practice lag compensator more than others compensator. We are good enough in PI controller design and so on, especially in Simulink. So now we need to keep the percent overshoot. So now we need to readjust the gain to have a 9.5 overshoot. Of course, for the steady state error for step input, this we cannot see it as it's in a ramp case. So you remember from root locus case. So if it's so, but for because anyway steady state always always equal 0 because the system type 1 for a step input. So for a ramp it's not the case. So I need to reduce the gain actually now. Okay. If I reduce the gain, okay, so this doesn't lead to me to the 9.5. Somehow it's 9.5. And this is my new design. So I have 0 at 1 and pole at 0.1. See, frequency at 0.1. I have a phase margin of 67 and gain margin of 24. And it gives me 9.5, around 9.5 overshoot. Okay. So also you could store your design if you are interested. But this is the exercise is about. So that's how we deal with. Okay. Let's see what I did myself. Maybe I take 0 of -10 actually, which then PC -1, which I don't really recommend to. Better to take the pole near the 0, near the origin, and then deduce 0. Okay. So I get this 1 because I have 1 and 10 actually, 1 and 10. Then I readjust the gain to regain the overshoot we want. In my case I did it and I obtain the overshoot I want with the different lag compensator. So the 0 and pole are at 1 and 10, not at 0, 1 and 1. But if you look to the time, peak time, for example, it's 4.48 seconds, so 4.5 seconds. And in this case it is 0.5. So it's much faster. The system is much faster than the system I have in my solution here. Okay, so it's up to you how you do your design, because I didn't specify. Both are correct in the sense I didn't specify requirement for the how fast should be the system. And here I have a gain of 254. In here I have a gain of 2.7. Okay, smaller gain, of course. Well, that's it about exercise 2. But here you may ask the question why I take PC equals 0.1 and therefore I deduce ZC. Well, always the recommendation was to have the pole near the origin and then deduce ZC. But actually there is a different way here. You can go for more structural way. You can go for, in case of frequency response analysis. So what is this way? How to pick the zeros and therefore deduce the pole? Actually, in this method, you will learn how to pick first the zero and therefore later on deduce the pole. And I recommend always doing it. Instead of choosing a pole 0, 1, okay, and then near the origin and then deduce the 0. No, I recommend you in frequency analysis to follow this methodology, this structured way in which they guide you how to find the zero, and based on it you deduce the pole, because the ratio between them is 10, as uh, we found in here. So the ratio between them is 10. So what this method tell you? First, of course, drag the body to get the desired phase margin equivalent to the desired overshoot, which we did at the beginning. So now let me delete, and then it was 605, right? So then we dragged actually the gain to get the desired phase margin, which is the desired overshoot. And remember, always we try to connect frequency domain to time domain, just for your own references. So 9.5 overshoot corresponds to a phase margin of 58. So this phase margin reflect the overshoot. Bigger phase margin, less overshoot. Okay. Uh, so that's step 1, which we did. Okay, let's see what's step 2. And this is done in first exercise here. At this case, the gain crossover frequency is 15.3. At this gain, the gain crossover frequency is 15 radian per second. So here is 15. At 0 decibel, you go and you get the gain crossover frequency is 15. Okay, we know it's 15, which reflect at the end. That's why we are looking to it, because it reflects the speed of the system gain crossover frequency. Okay, so this is step 1, easy done in first exercise. So what's next? What's new? All right. Then they said it's a good practice to add a phase of 10 degree to the desired phase margin. Our desired phase margin is 58.3, because this 58.3 phase margin, it leads me to my desired overshoot, which is 9.5. But here they are telling me it's a good practice to add a phase of 10 degree to the desired phase margin. Therefore, my desired phase margin is 58 when designing, say 58 plus 10. Because you remember lag compensator, when you want to add a lag compensator, you have a 90-degree lag in phase. So to compensate for this phase lag. So it's a good practice to add a phase of 10 degree to the desired phase margin, because later on when I add the lag compensator, so then I have some safety margin. So I end up at the end having a phase margin of 58. So So it's good practice to add a phase of 10 degree to the desired phase margin, which is a 58, to compensate for the phase angle contribution of the lag compensator. So we find the gain K that gives a phase margin of 58 plus 10, which is 68. Then we retune the gain K until we get the phase margin plus the 10. Phase margin plus 10, which is this one. It's obtained at a gain of 375. Well, you can retry it yourself until you get 58.3 plus 10. So now they telling it. So I'm giving you the value 375. Okay, so then according to them, it's a good practice to find the gain K that give the phase margin plus 10. Okay, the gain crossover frequency now is 9.9. That's the gain crossover. Why I'm interested to look at the gain crossover frequency? We need to look at them because also those at the end will reflect your location of your poles and zero of the lag compensator. So here I will tell you now how to choose the zero and therefore reduce the pole. By looking to the frequency now, which is 10, around 10, add a zero a decade below the gain crossover frequency, so 0.1. So now I add a zero at 0.1, at 1 actually, because this is 10, 10 over, decade below 10 over 10 is 1, okay, or 0.9. So then second step is to add a zero decade below the gain crossover frequency that's obtained by increasing the phase margin of 10 by 10. Then I add a zero, I go and add 0 at 10. Alright, so where is my root locus? So I'll go and add 0, real 0 at 1, actually at 1, or 0.99. Okay, I'll keep it this way. So what else? Then add pole. So now once we know the 0, then the pole is the ratio between them. ZZ over PC equal 10. That's the ratio that we obtain. Then we can conclude PC, which is 0.1 or 0.09. 0.1. So then I add a 0, add pole, add, no, I don't want to add it this way. So add real pole now at 0.1. Pay attention, this is the 0. Here's the pole. Alright, so that's how we select the 0 on pole. So you select first the 0 in this method, then you reduce the pole. Then you readjust your gain to retrieve the desired phase margin you desired overshoot you wish, which is 95, which is 9.5. Like in this case, I get it with a gain of 260. Well, okay, so it gives me 9.5. Okay, so you can play with to get your desire, and therefore this is your design. So now this is another way which I recommend actually to go with. Also, I want to point out, like, you can use the design requirement as we did in Rotlocus. Here I have a gain of 605, which corresponds to 9.5. But anyway, so what are my design requirements? You can go to the design requirement menu. You have upper gain limit, lower gain limit, gain and phase margin. I know, like, my phase margin is 58.3, right? My phase margin is 58.3, which is the one here. And gain margin, I'll keep it as it is. I have no constraint on how fast the system will be. Let me keep it, but basically I can take it out if not needed, so I keep only the phase margin. Okay, so then I have this constraint. And phase margin, also I have a constraint on kV, which is tenfold the old kV. So now, remember when we did the calculation, kV is the new kV is 168. So, and remember, it's a type 1 system. So kV 168, which it will cross at a frequency here equal to kV at 0 decibel. Okay, so I can draw this line, and this is my design requirement now. I can draw the slope here, which will be my design requirement. Why? Because this is satisfy my kV, the kV that I want. So the system should cross over on 168, which is your new kV. Then I can have a new design requirement, and this design requirement are, let me put a frequency here of, if you wish, maybe take it this way, frequency here of 168, and magnitude of 0, of course, because 0 decibel at this frequency, and the slope of how much? Slope of minus 20 decibel per decade. Minus 20, again, this is, I want it to be 0. Okay, minus 20. Okay, it changed. Basically, because I want maybe to put another one. Like, let me put here a frequency of edge start and edge end, and therefore we can reduce by default to reduce the slope. So edge start is, if we take 16.8, so decade below, and therefore decade below then should be 20. Good. And this is 0, and this is minus 20. Alright, so now it seems right. Okay, so here is your design requirement. If you wish, you can keep drawing it if you have a ruler, or well, let's see how to design a controller now. Well, we designed the controller actually, but let's add it as it was, because we did the design before. You can add it as it is, or actually what you can do now is just try to play with it this way to make sure you are satisfying the requirement. Even so, this is not really satisfying the requirement. Okay, better to delete this. Okay, maybe if you wish, I can make it even longer, right? So how to make it longer? Edit. Maybe instead of 16.8, I put it 0.168, 0.168, so divided by 100 means it's 60 decibel per decade. So it becomes longer. So you see now, this is my slope. So means I'm not satisfying really my requirement this way. So I need to reshape it to get something similar to this. Maybe you start adding 0 and pole. We know if you add pole, this is will shift up. 0, so will shift plus this, plus 20 decibel per decade and so on. So the controller we found, if you want to integrate it directly, is has 0 at 1 and pole at 0.1. Alright, that's what you find. So you see it's like it's 10 point something. We need to recheck this design requirement, if it's met, but basically at infinity this should be kV. Like now, if I should go to 168 to here. Alright, this should be, because this should be the 168, but it doesn't seem to be. This is the 168 radian per second. Let me recheck it. Check my design requirement. Seems like edit. Yeah, it seems like not the case. So 0 decibel. Okay. Alright, so now it seems to be okay. Yeah, it sounds good now. Maybe I can prolongate it more just to make sure it's coming to here as well. So edit, maybe instead of put 0.00020, so 60, 80, 100, right? 20 decibel, so 80, 20 decibel, 100, and this is 0, and the slope is minus 20. Slope is minus 20. Alright, seems fine. This is your design requirement. So now if I keep approach it, this way, so you have a phase margin of 58.2, but this is your design requirement. You can re-verify it. It seems okay. Okay, so then you cannot go overpass it. If you overpass it, the system will overshoot more than required, and also your KV is not anymore the one you want. This is give you the KV that you want. 168. If it's KV 168, and overshoot is of 20. Okay. Well, think if I have more precise KV, maybe better. Maybe KV is not exactly 168. Maybe it is 104 or so. Because if you want to have 9.5, if you want to have 9.5, basically your gain is 260, right? 260, and this is if you want to look at it actually how much it is. Somehow here 0 decibel here is that's the frequency here at 0 decibel, which is what 7. No, so this is the frequency. Okay, they take this as 168, but the 168 should cross the 0. That's what's crossing the 0 now is almost here, which is somewhere here actually. Okay, maybe 100. If you take the 100, let's see. Let's say 100. Maybe somehow close to 100. Alright, let's say KV is around 100 now, not 168. But at the end, this is 20 decibel. So this 20 decibel crossing it here. 20 decibel per decade. This is essential because it's keeps the same slope. So you can do it using this design requirement. I recommend to, because you know designing the requirement in body diagram, it's not it's not familiar with as in case of root locks, and so it may take more time. But it's good to know about it. But then don't recommend to go this way. Okay. We have KV equal 168, but and it's supposed to be accurate. So it's supposed to be 168 actually. But it doesn't give me the 9.5. Give me around 12, which is considered as acceptable. Okay. Also, if you want to keep it at where it was, somewhere not here of course, but whatever it was, so it gave me around 12 overshoot, which is considered as acceptable. So you can follow same analysis. But again, I don't recommend you to do the design requirement. Just for you for verification, we can be sure that it's 20 decibel per decade and crossing over here with the KV value. Good. That's it for exercise 2 and 1. So now we'll record for exercise 3. Okay, now still having the same system, but they ask us to design a lead compensator for it. So given the figure below, it's the same system as before. We are doing shaft position control, so we control the position of the shaft. Oh, that's the system, etc. etc. So design a lead compensator to yield a 20% overshoot and a KV equal 40 with a peak time of 0.1 second. So now it's okay to have a little bit more overshoot, but we allow overshoot. So instead of 9.5 previously in the lag compensator, it's okay to have it 20%, KV 40. So before KV was 168. So 168 means a small steady state error, much smaller than this one. Steady state error is 1 over KV. When kV very high, the steady state is very small. So also it's okay to have of the ramp input some little bit steady state error, but with a peak time of 0.1 second. So we want to design lead compensator PD to make the system faster. So we put now a constraint on the speed of the system, on the peak time. Here we had a peak time of 0.52, alright, and only an overshoot of 9.5. So now it's okay to have overshoot, kV not so high, so steady state error not so low, but with a peak time we want a system faster. Even if they don't ask us to design a lead compensator, we can predict it should be a lead compensator, so equivalent to a PD controller. Okay, we'll design a lead compensator. How we go over this? Well, first you should know the lead compensator, how it looks like. Is as in root locus, so it's not like something new for me. So are familiar with the lead compensator. So if that's a spline, so it's a lead, so the zero dominate the pole. Okay, S plus Z over S plus B. And if it's a frequency scale, assuming this is a 0, 1, okay, so you'll have the 0 because it's smaller. Of course, this is minus, than the pole. Alright, on the body plot, because you have the x-axis, you have omega, and P and Z are the frequency. So we need to design it to satisfy our requirement. Also, we know, because already in the course I introduced to you the relationship between time domain and frequency domain. We know the peak time is somehow related to the speed of the system. Basically, the peak time or rise time, if you wish, somehow related pi over omega d, and we know that omega d, so the omega d is inversely proportional to, so the frequency is inversely proportional to the peak time, of course to the rise time as well. Omega d is also related to omega n, the gain crossover frequency omega n, and the damping ratio. So they are all related then. Omega n is the gain crossover frequency, the natural frequency of the system. Okay, so from here you can know that they are connected, so it's speed related. Also we saw that if we increase omega n, the speed will increase, so the peak time or rise time will decrease, system becomes more faster. So the first step here they are teaching us, the first step in designing the controller, the compensator, is to satisfy the velocity constant error kV. Okay, so we need to satisfy first the velocity constant error kV equal 40. Then a lead compensator to satisfy the overshoot and the peak time required. So let us first use gain controller to satisfy the velocity constant error, then lead compensator to satisfy the overshoot and the peak time requirements. So g of s equals my transfer function, which we know. Then for kV known, can I find k? And this k controller, this k gain, this gain will lead me to steady state error of 1 over 40. kV equal 40, limit when s tend to 0 of s, u of s, the open loop, which is this one. So then I can find k, because it's only unknown, and k equal 1440. So now I go to my system I will take out the lag compensator and 1440. This 1440 is what give me the steady state error I want. It give me a KV equal 40. Alright, for a ramp input, of course. So with this K, the system has a phase margin of 34.1 degree at a gain crossover frequency of 29.6. Okay, 34.1 degree phase margin at a gain crossover frequency at 0 decibel is 29.6. Alright, this is the first step in our design of the lead compensator. What's the second step? Well, second step, we need to design the lead compensator to achieve an overshoot of 20%. So overshoot of 20%. Okay, so what we'll do now, maybe I can store this design. So we could remember it. 36.8 overshoot at this amount of time. That's the phase margin, frequency response, gain margin, frequency, gain crossover frequency, phase crossover frequency. Anyway, this data I recorded them in the Word document for you. Yeah, they are here, but because we will use them later for the next step. So now I designed to get an overshoot of 20 as per required. It's required to have an overshoot of 20% with a peak time of 0.1 second. Overshoot of 20. This is 17. This is 19 point. So maybe not 860, but something close to maybe 885. So you can play with, just for the sake of time, I already did it before. 20% overshoot. So this 20% overshoot, my desired overshoot, is obtained at a gain of 885. But we know to have KV equal 40, my gain should be 1440. So now my gain is 885. Well, but at this gain, at least I know that I have the overshoot required and I have the peak time required. 0.135, which is somehow, okay, we are close to our required, which is 0.1, which is considered as acceptable. So why we need then to use this? So we start from here. That's the second step. We need to follow them step by step, design guideline. So now it's easy, so you know how to go. Basically that's what I did, and I record the value. So overshoot of 80 corresponds to a phase margin of 48. So then what's the third step? Third step telling you starting from a gain of 1440. So why I want to return back to the first thing I was doing. Well, you will see later on why we went to 20%, this one, and why do we need it, for what reason. Because this is my design goal at the end, okay, to achieve this overshoot in this peak time. So starting again from the 1440, which lead me to higher overshoot and the phase margin of 34. So now in step 3 they are telling you starting from here and your goal is to move from here up to the below, up to the your design requirement. So you need to move. So your goal now is to move from step 1 to step 2. And here is the trick. So now, which controller or how to put the controller in a way you can move from this state where you are satisfied your steady state error. You are satisfying your steady state error with kV equal 40. You need to keep the steady state error you wish, but at the same time improve the overshoot. So how to reduce the overshoot? By increasing the phase margin from 34 to 48. By increasing it from 34 to 48, I'll be able to reduce my overshoot from at 34 I have overshoot of 360. So from 36 to I can reduce it to from 36 to 20%. And this is by increasing my phase margin from 34 to 48.2. So you need to move from the first situation to the second situation. So find the controller to lead you to this. So if I want to move my phase margin, I increase the angle. Alright, I want to increase this angle. What we do, you look to the 20 radian per second here. So at 20 radian per second, I try to design my lead compensator, which give me a phase lead, so I can add an angle on this angle of 34 degree. I can add an angle to reach the 48 degree. So I add a lead compensator. Here is the trick. I add a lead compensator in between. So if this is my frequency body plot scale, so this is the 20.8. If this is the gain crossover frequency, which is 20.8 radian per second. So you need to add lead compensator in between. So your pole and zero in between. So which first, the pole or zero? It's a lead compensator. And remember, lead, it's the past. It is the past, right? So it is equivalent to PD. So then your zero is here and your pole is here. Okay. So then now what you will do, you will go and add zero and pole to the right and left, as in this schematic here, to the right and left of your omega C, the omega C that you get it here at 885, which is your design goal, that reflects your design goal. In a way, so you add the zero and pole and you try to play with them, the zero and pole, until you satisfy your requirement. Alright, and that's what they are telling you to do in this step. Add a pole to the right of the 20.8 and 0 to the left of the 20.8, because this is a lead compensator. Then alternatively move them to obtain an overshoot of 20 and a peak time of 0.1, which is your design requirement. Or in another word, a phase margin of 48 and a cutover frequency of 20. Because the phase margin is related to the overshoot and the cutover frequency is related to the time, to the speed, how fast it is. So let's go and add it. I'll go and add 0 to the left of omega C and a pole to the right of omega C. 0 to the right of omega c, which is 20.8. So where is the 20.8 first? If you wish, let's find the 20.8 first. That's 10, 11, or 10, 20, 20, 30. So 20.8, like 21. Okay, so somehow here. Right? Well, somehow here. So you need to add them to the right and left of it. So then I add 0 to the right of, okay, you can put it anywhere, it's fine. So this is the 0 to the right of, to the left. And so now I can take this because the scale is shifted, no problem. So that's the 0. You still have the 20, you can understand where it is. 10, 20, around here. So now I go and add the pole. If that's 20, maybe I add my pole in here. Alright. Now you need to play with the pole and 0, drag them until you satisfy your requirement. So how to move the pole and 0? Remember, the 0 will increase your oscillation this way, because the 0 here, it will lead you to, at the end, a stable system. And here is the pole. And you keep tuning, but make sure you're still in, that's a 20. So you know, still I'm in between. So you can have an overshoot of 18, which is now, it looks like I'm fine. Overshoot of 18. So let's see the question again. An overshoot of 18 and a peak time of 0.1. Well, my peak time is less than my overshoot is 18, so that's 20. Maybe I can. So this 22. Maybe this is too much. Yeah. And the peak time is very slow. Now the system speed, you can see it's a slow system. So alternatively, you can do it using calculation. So I'll show you the method now. But before, let's see the value I obtained, like the gain and the lead compensator. So here it is, and also in your book, in your Word document, you have somehow different one, but also it satisfy your requirement. It's saying like, let's read the requirement again, with a peak time of 0.1 second. So this is maybe, so I have it too much smaller than 0.1 second. Okay, in our case. So let's see the alternative method. Well, it's a very guided tutorial here, so I'll go with you over it. So there is some step you need to follow, and you get your result. And this is a calculation method. Okay. If you don't want to alternate your pole and 0, you can use this solution. The previous step 3, using the seesaw tool is replaced by the following. So that means step 1 and step 2, they should stay the same. Step 1 and step 2, you do them and you extract the information you need. And now instead of doing step 3 this way, adding the zero and pole around the 20 radian per second and try to place them, adjust them to satisfy your requirement, what we'll do in this step is the following. We need to go from 34.1 degree phase margin to 48.2 phase margin. So that's why it is a lead compensator. From 34.1 to 48.2. Here what they are saying. So a lead compensator with an angle of 14.1 degree must be added. A lead compensator with that angle should be added, so then I can add an angle to the 34 to reach my 48 and therefore my design requirement. However, it's a good practice to add a correction factor of 5 degree to 12 degree to compensate for the lower phase margin at high gain crossover frequency, because also we need to increase the speed of the system using lead compensator. Your gain cutover frequency will be shifted to the right, means you will increase your system speed, system will become faster, and by doing this you are lowering the phase margin as well. So to compensate for this, because we know it's a lead compensator, so to compensate for this effect, it's a good practice to add a correction factor to compensate for the lower phase margin at high gain crossover frequency between 5 to 12 degree. So here I choose to add 10 degree. So you can choose to add anything else. I choose 12 degree, recommended usually between 5 to 12. You added 10 degrees and 14.1 plus 10 is 24.1. And this is step number 3 now. Step number 4 is to find the ratio between the zero and pole, which is equal to alpha, and how to find it using this formula: alpha equal 1 minus sine phi m 1 plus sine phi m, where phi m is your difference in phase margin, which is at the end, after adding the correction factor, you get 24.1. So alpha is 24.1 degree, you convert it to radian and you insert it into the sine in radian, you get alpha. Okay, so now I have alpha. What's next? Your fifth step is to compute the gain we call Km, and this gain equal minus 20 logarithmic decimal of 1 over square root of alpha. So minus 20 log 10 of 1 over squared of alpha, which is 0.42. So you get Km. Sixth step. Step number 6 is separately use Bode plot of this function, which is basically what this function is the gain that you obtained in step number 1. Remember, 1440 times your open loop transfer function, and you draw the Bode diagram. How to draw the body of G? You say body of G, you get the Bode diagram of it. But this is the saying step number 6 that you need to follow. And this Bode plot is used to find omega n, which is the cut over frequency of the open loop system after adding the lead compensator. Okay, so we need to use it. We use this Bode plot to find omega n, and omega n is by design, we will design it to be the cut over frequency of the open loop system after adding the lead compensator. So now what I did here, as you see, I draw the Bode plot of this simple transfer function on MATLAB, and I get the cut over frequency, which is omega n. At 0 decibel I have a frequency of 38.8. So now my cutover frequency is 38.8 radian per second. Then here what you will do is you want to place a pole and zero. If that's omega n, in here you want to place a pole and zero to the left and right of it. This is, remember, a lead compensator, so derivative term dominate, so you have zero here and pole here. So the pole and zero are to the right, pole to the right and zero to the left of omega n respectively. Well, so do I need to do the same then as before? No, of course not. So what's the difference now? How to get the zero and the pole? Using the formula below. 0 equals square root of alpha omega n, and alpha we already found it before, and omega n we just found it now. So we can find z, and therefore we can deduce p, because the relation between zc over pc equal alpha. So if I get z, I can find p, and because I have now z and p, and this will be my lead compensator. Alright, so this is my lead compensator in this case. So let's insert it into MATLAB. So now I'll delete, and then I add lead compensator with a 0 at 25.14 and a pole at 59.87. And so which method do you want to use? The hands-on method, or the calculation method, or just you put your pole and zero and you alternately change them until you reach your requirement? Well, this method, the calculation method, is recommended if you have a program, MATLAB program, in which all those calculations are done. And usually researchers try to do this way. So because it's easiest done, trying to move the real, even if it is guided movement, it's not like anyway, so you will reach your goal fast because it's guided movement. That's like you are closing your eyes and you move the pole and zero for the lead compensator. It's not the case. So you are moving them around a frequency and in between this frequency. So this is what I get with this compensator that I calculated by hand. I obtained this response, which had an overshoot of 22 point something and a peak time of 0.07. So I can consider it as acceptable and keep it this way. It's alright. Or I can if not consider it satisfied, then you can slightly interact with the location of the pole and zero to achieve more precise results if needed. Well, I can consider my results as enough. Otherwise, you can slightly interact with to achieve more precise results if needed. And this is all for this exercise. So in this exercise, we started first by working with only gain and designed only gain, right? Then later on designed a lag compensator. Then now we are designing a lead compensator. So we saw for the same exercise, we saw different type of them. So then if you wish, you can compare the lead or lag given same specification. Of course, they serve different functionality. So one to speed up the system, other to reduce the steady state error. So here you have like we sacrifice on the steady state error in order to speed up the system. Also we sacrifice, well, I don't want to say sacrifice on the overshoot, but here we have overshoot of 20, more than what we had when we designed the lag compensator anyway. So This is, you can say it's same exercise, but it's divided into 3 parts, or if you wish, that's why here you can see them as 3 exercises, 3-part exercise. Actually, it's the same exercise if you wish. Then now we will learn how to design lead lag compensator.